Welcome. In this video, we'll be going over loop gain analysis for feedback circuits. So loop gain analysis is an alternative analysis method than using shunt, series, shunt, series, shunt, and so forth. So sort of trying to identify one of the four feedback structures and then using analysis based upon that. So loop gain analysis is an alternative method for this, and instead of that, and it is closely related to return ratio approach for feedback analysis, but rather than using the return ratio, I use something called the loop gain in this. So let's get started. So as I mentioned, we'll be looking at a hand analysis technique or an analysis technique for doing loop gain analysis on circuits. So there's generally three main things that we're trying to find in feedback circuits that we'd like to do some analysis for. And the first would be closed loop gain, or the transfer function of the system. The second would be the port impedance, to find the input impedance or the output impedance, which generally you'll find will change depending upon the feedback and the loop gain that we have. So as the loop gain increases, the input impedance or the output impedance will change proportional to the change in the loop gain that we have. Finally, the last thing we'd like to look at is stability analysis. We'd like to know how stable is the system with feedback. So how stable is it? And for that, we can look at phase margin and gain margins. And so we'll look at that as well. In this video, we're going to be focusing just on the first one. So we'll be focusing on closed loop gain. And in other videos, we'll be looking at the other two aspects. So as I mentioned, in this video, we'll be looking at the closed loop gain, and we'll be using something called the asymptotic gain model to make our life a little easier, to help us find the closed loop gain for practical feedback circuits. So let's start off, and we'll look at the closed loop gain. Let's start off by looking in the ideal case, which is not necessarily that practical not necessarily that useful for practical circuits. So if we just look at the ideal case, we have our input, X sub S on the left, our output, X sub naught. Now as before, we're allowing that X sub S is an input voltage or current. So it could be one or the other. The output is X naught, and the output is either voltage or current. And as we had before, if whatever the type of unit that X sub S is, then the feedback signal and the error signal will all be the same type, either all voltage or all current. Now in this ideal case, we have that A and beta are both unidirectional. So in other words, we see that there's a signal that flows from X sub I to X naught, but there's effectively no signal, perhaps I should draw that smaller, there's effectively almost no signal or zero signal going in the opposite direction. Similarly, we have for beta that there's a signal going in this direction, but we're assuming the backward signal is effectively zero. Now it turns out for this one here in the amplifier, it is often quite small. But in this case here, that may not be the case. Now in this circuit, before we move on, we can find, and we've seen this before, that the gain from the input to the output is given by this formula here. It's just equal to A divided by 1 plus A beta, or divided by 1 plus the loop gain. Remember, we generally call A beta the loop gain for the circuit. As I mentioned then, while this could be a useful analysis approach, it's not generally practical. In practice, A is mostly almost completely unidirectional, whereas beta is generally bidirectional because it's built with a passive circuit. It's built with a couple of resistors or capacitors and resistors and so forth. So it's a passive circuit. So what we find is a much better model to model this is this system here shown, where we actually now have broken up beta into two parts. beta 1, the feedback part, but also feed forward part to account for the direction going from this direction into the beta network, and the feedback part is going in this direction through the beta network. So we've broken up into two parts here. So we now have beta 1 and beta 2. If we do some analysis on this, we'll find that again, the transfer function from the input to the output is now given by this equation over here. So it's equal to A divided by 1 plus the loop gain, which is 1 plus A times beta 1, plus beta 2, which is this value, divided by 1 plus the loop gain, 1 plus A times beta 1. And so that becomes a much better representation of a practical circuit. Now, we know the loop gain, L, we've said is the multiplication of A beta 1. So what we're saying here is that the loop gain is the gain around this loop. And we see that's going to be multiplying A times beta 1, where beta 2 is not in the loop here. It's going directly from the input to the output. So it's the feed through portion. Now we also can see that from this equation here, in the case where L goes to infinity, so if we have L going to infinity, then 1 plus A beta 1 is becoming very, very large. So A beta 1 is becoming much, much greater than 1. And so this whole term here becomes 1 over beta 1. This term over here, beta 2 doesn't change. A beta 1 is becoming very, very large. So this term here goes to 0. So as L goes to infinity, this reduces to 1 over beta 1. So what we have is that as L goes to infinity, we have that the transfer function here is just 1 over beta 1. So let's define a new parameter. That's why we call this the asymptotic gain model, because we'll look at the asymptotic gains when L goes to infinity and when L goes to 0. So we'll define a new parameter called A sub L infinity. And that's the gain from the input to the output when L goes to infinity. So when L goes to infinity. So it's the transfer function when L goes to infinity. And as we've just found, that's going to be equal to 1 over beta 1. So we'll define this new term here, A sub L infinity. So we can, from above, we can see then that this beta 1 is just equal to 1 over A sub L infinity. Now, if we want to see what does A become here, this A term. Well, if we look at, we already know that L is equal to A times beta 1, which means A is equal to L divided by beta 1. We just said beta 1 is equal to 1 over A times A sub L infinity. So the A term is actually equal to L times A sub L infinity. So we have a new way to write A and a new way to write beta 1. Finally, we also have, because we want to look at the asymptotic gains, is what happens if L goes to 0. So if L goes to 0, A goes to 0. And again, going back to this equations up here, if A goes to 0, this term goes to 0. This term becomes beta 2. So we see that the gain, or the transfer function, will become just beta 2 if A goes to 0, or the loop gain goes to 0. So what we can define now is that A sub L 0, so the gain through the system when the loop gain goes to 0, is just equal to beta 2. And that becomes the new parameter we can put in here. So we can redraw this entire block diagram, shown like this, where now we're using the terms L times A sub L infinity for A, which would be here. We're using the term A sub L infinity, which is 1 over A sub L infinity is put in for where beta 1 was. We're also using A sub L0, and that was where beta 2 was. If we find the transfer function then for this block diagram, we have that the gain from the input to the output is now given by A, which is given by this, divided by 1 plus the loop gain, which is the gain around this loop, plus A sub L0, which is here, divided by 1 plus the loop gain. So you can do the analysis and find that this gives you the transfer function. So now, this gives us a method to find our closed loop gain of a system. Remember, our goal is not to find the closed loop gain with this block diagram, but it's to find the closed loop gain of a circuit, transistor level circuit. So we have that the closed loop gain is now given by this formula. And just as a sanity check before we move on, let's make sure that our loop gain here is equal to L. Well, our loop gain is going to be this term, which is L times A sub L infinity, times 1 over A sub L infinity. And so if you do that, we see we're just multiplying these two together. And then we'll be able to cancel out the two A sub L infinities, and we get L as expected. So what we have then is we now using that block diagram is we have a general formula for a feedback circuit that the closed loop gain of the feedback circuit is A sub L infinity. So all we've done here is brought out this term separately out of the bracket. And we'll also bring this out of the bracket. So that's all we're doing in this step. So we have that A sub L infinity times L divided by 1 plus L plus A sub L0 times 1 divided by 1 plus L. And what are these three terms? Well, these three terms is L is the loop gain. So if we can look at a circuit and find its loop gain, that we set our signal, our input signal equal to 0, then that will give us our value for L. We also need to be able to find A sub L infinity. And that will just be the transfer function from the input to the output if we can make L increase to infinity. So we imagine that the loop gain goes to infinity, and we find the transfer function then for the circuit. Then we also find the transfer function from the input to the output if we make the loop gain go to 0. So if we force the loop gain to 0, we find that transfer function that will also have this value. So we do these directly on the circuit, and once we have all three of these, we can substitute that into here, and we have the closed loop transfer function for the circuit. So this just says that to find the closed loop gain, we find L, A sub L infinity, and A sub L naught. To find these, we're going to be breaking our feedback loop, and temporarily, just to be able to find these three values. So we need to know how to break our feedback loop. So here's our feedback system, and generally we will break it into one of two locations. So we either break it just before the amplifier, after the amplifier. Generally, we don't break it in the bottom part. We could for parts of these analysis, but if we want to be consistent for finding all three of these values, L, A sub L infinity, and A sub L0, it's best just to break it in one of these two locations. So we don't have to re-break it for different analysis or for different finding different values. So as I said, we typically break it in either break 1 or break 2. So either here or here. So what does that mean to break the circuit? So what we do is, well, let's say we decide to break it in this location here. So what we'll do then is, first off, we notice that the direction of feedback is here. So the direction of the signal path is going from left to right. So here we have the direction of the feedback, so the direction of the signal path. And what we'll do is, when we break it in this location, is we'll first find the impedance looking to the right, and we'll call that Z1. We'll also find the impedance looking to the left, and we'll call that Z2. In both of these cases, we'll make the input signal x sub s equal to 0. So whenever we're finding these input and output transfer functions, or impedances, we set x sub s equal to 0. When we break it by just taking this Z2, we put on the right side, so the loading is still correct. We take Z1 and we move it over to the left side, so its loading is correct. Because remember, we saw this loading, looking this direction, we saw Z1, and looking this direction, we saw Z2. So that's why we have to place them from this left to right and from right to left. So we've left all our impedances that we're looking still to be the same. And as I mentioned, when we find these impedances, we always let in our input source equal 0. And once we've broken it, we can then find these three values. So we want to first find L. To find L, we've broken our loop at this location here. So that's been broken. We apply a voltage V sub t, an ideal voltage source V sub t, and we find the voltage that occurs back across the impedance that we've introduced. Remember, we've introduced Z1, we've moved it over, and we find the voltage that we see across that impedance. And so then, by definition, the loop gain, L, is just minus VR divided by Vt. And so it's the gain from Vt all the way back to Vr. So going once around the loop. So in other words, if we're breaking it at this location, we're finding the gain around this loop back to this location. The negative sign is there because we've assumed that the negative sign is already taken into account here. So there's already negative feedback in this, so L should always work out to be positive. So we've added this negative sign over here to account for that, which means that L should be greater than 0. Now notice that in this case, Z2 is in parallel with our ideal voltage source. So really you didn't even need it in this case to calculate what Z2 was. There was no value to it because you placed it over here, but you won't need it in any of your calculations. So just for finding L, you can leave out finding Z2 if you don't want to, because Z2 is in parallel with the ideal voltage source that you've introduced into this circuit. Now, next one I want to do is find A sub L infinity. So in this case, we want to make the loop gain go to infinity. Well, one way to do that is to introduce a voltage-controlled voltage source, an ideal voltage-controlled voltage source. So we've introduced that here, where the voltage control is A sub V, and it's multiplied by Vx, where Vx is the voltage seen on the left side over here. So we've just introduced, we've broken it, but introduced an ideal voltage-controlled voltage source. And in this case here, if we want to make L go to infinity, we can now just make A sub V go to infinity. So by definition now, A sub L infinity will be the gain from the input to the output when AV now goes to infinity, because AV going to infinity will make our loop gain go to infinity. So we've introduced an artificial gain stage into this circuit temporarily, just to find A sub L infinity. Now, we can use a few things here that will help us do our analysis. Because we know that this gain A sub V has gone to infinity, that means assuming that the voltages in the remaining parts of the circuits over here somewhere are finite, then this voltage here must be going to 0. So V sub x must be going to 0, which then if V sub x is going to 0, then I sub x must also be going to 0. So whenever we introduce this A sub V and we make A sub V go to infinity, then V sub x is going to 0 and I sub x is going to 0. And we can use these this knowledge to make A sub L infinity much easier to find. Also, as before, because Z2, once again, is in parallel with our ideal voltage-controlled voltage source, we could leave out Z2 in this case as well. We don't make use of it. It's really the final case where we need to make use of it, A sub L0. And we'll see examples of this in a little bit. So finally, we'd like to find A sub L0. That's the third part we need to find. So in this case, we break our circuit as we did before, and we put in the two appropriate impedances on either side, and then we just find the gain from the input to the output. That's defined to be A sub L0, and we have the break here, so the loop gain has been broken. So because we've broken the loop gain, L has gone to 0, so we've made L go to 0, and we now just find the transfer function from the input to the output with this break in the loop gain. So to recap, we've been looking at methods to find these three values here, L, A sub L infinity, and A sub L naught. Once we find those three, we can find A sub CL by substituting into this formula here, where we have A sub L infinity, L, and A sub L naught. So let's look at some examples on how we can apply this to circuits. So here's our first example here. So in this case, we have a inverting amplifier configuration. We have our input V sub S on the left, the output V out, and we're going into an inverting gain stage with an op-amp. In this case, we'll assume that the op-amp has a gain, finite gain of A sub naught, but otherwise it's an ideal op-amp. We'll assume that A sub naught is equal to 50, so it only has a gain of 50 in this case, which is obviously low for an op-amp, but this will be useful for feedback. If we make it too high, then we'll just see the resultants minus R2 over R1. We'd like to see what it actually would be if we had a lower gain in here. Might be a single stage amplifier circuit for this or something. So what we'd like to do is break this feedback loop, and we'll break it at this location here where the X is. And then we'll have to find the impedance looking in to the negative terminal of the op-amp, and also the impedance Z2 looking backwards into this circuit. So what we see is that we'll find that Z1, because it's looking into the input of a op-amp, we've assumed it's an ideal op-amp, so that goes to infinity. So Z1 is just going to be infinite. For Z2, here, we have that it's just going to be, first off, we zero V sub S, so we set that equal to 0. And we also know the output impedance into an op-amp will be 0, because it's an ideal op-amp once again. So this appears as though it's ground at this node. This looks like ground at this node. So for Z2, we just see R1 in parallel with R2. So we have this result here. And because R1 and R2 in this case is 10K for each, Z2 is just equal to 5 kiloohms. So then we need to find L, A sub L infinity, and A sub L naught. So for L, we break the X, we break that node, but we also introduce a new source here, V sub T. So an independent source, we set V sub S equal to 0, so that just becomes a ground at this node. And so we're finding now the gain from V sub T all the way back to VR. So it goes around the feedback loop here. So we want to find the gain VR divided by VT and negative. So if you recall, the definition of L is minus VR over VT. So what we have is, if we define this node to be V1 temporarily, then we have that the gain from VT to V1, well, VT is just going to appear right at this node on the negative terminal, so it'll be a gain of minus A naught. So just be the gain through the op-amp itself. And we also need the gain from V1 to VR. Well, that's just a resistor network with R2 and R1 and Z1, but Z1 is infinite. So it's really just a resistor divider network between R2 and R1. So we have that V sub R will be V1 times the resistor divider network of R1 divided by R1 plus R2. So if we make the substitution of V1 into here, we see that VR can also be written as this. So then we can now, using this term on the right, that we have VR, we have an equation with respect to V sub t. We can substitute or divide through by Vt, put a negative sign in front, and we finally find that the loop gain is given by A0 times R1 divided by R2. A0 is equal to 50. R1 divided by R1 plus R2, because they're both 10 kilo ohm resistors, works out to be 1/2. So the loop gain is 25. And L is greater than 0, as it should be. Otherwise, we would have positive feedback rather than negative feedback. So L should always be greater than 0 for negative feedback. Next thing we need to find is A sub L infinity. For that, we have the same break, but in this case now we've introduced a voltage-controlled voltage source here, and we have a gain of A sub V. A sub V is multiplied by Vx, where Vx is the voltage over here. So we've effectively made a very large gain from this node to this node, and a gain of infinity. So Vy will be equal to A sub V times Vx. Now, feedback, because it's negative feedback, Vout will still remain finite. Remember, if A0 went to infinity, we'd have an ideal op amp, and we'd have a virtual ground at the negative terminal, but Vout would still be finite. So Vout with negative feedback, with proper negative feedback, even though we've inserted a gain here that goes to infinity, Vout still remains finite. So if Vout is finite, that results in Vy, this location, also being finite, because it's divided by A0. The gain from Vy to Vout is just minus A0. So Vy is also now finite. But if Vy is finite, and AV has gone to a gain of infinity, that implies that Vx over here should be going to 0. And if Vx is going to 0, then Ix must be going to 0. So this is the key part here. By AV going to infinity, we know now that these two are true. Vx goes to 0 and I sub x goes to 0. Now, making use of that, we can see that the current I sub 1 here is equal to Vs minus the voltage at this node, but we just said the voltage at this node is Vx, which is 0. So it's Vs minus 0 divided by R1. So now I have the current I sub 1. We also have that we just showed that I sub x goes to 0. If I sub x is going to 0 here, then I2 must be equal to I1. So all of this current must flow through here, since Ix is equal to 0. Now we have that since the output voltage over here will be 0, will be this voltage here, which is 0, minus the voltage across this resistor. The voltage across that resistor will be I2 times R2. So we have that the output voltage, the out, is equal to 0 minus I2 times R2. We already know that I2 is equal to I1. We have I1 over here, so we can then write this equation, that it's 0 minus Vs over R1 times R2. And that implies that V out over Vs is just equal to minus R2 over R1. Sorry, this should be a, right here should be a arrow. So it's V out over Vs is now equal to minus R2 over R1. That implies that our A sub L infinity, which by definition is V out over Vs as L goes to infinity, is equal to minus R2 over R1. And in this case, because R2 and R1 are equal to each other, it's just equal to minus 1 volt per volt. Now we have A sub L infinity. The last thing we need to find is A sub L0, and then we can find the overall closed loop gain. For A sub L0, we've broken the loop here. And we have that Z1 was equal to, went to infinity. Z2 went to 5 kiloohms. Turns out that's not that important in this particular application. But the main point here is that because we have an ideal op-amp, we know that I0, the current going to this negative terminal is equal to 0, which means the current going through this impedance Z2 is equal to 0, which means the voltage here must be equal to the voltage down here, so the V2 must equal 0. If V2 equals 0, then V out must equal 0. Remember, we have 0 output impedance over here as well. So it's forced V out to be 0. So what we have is that V out is equal to 0, so that means the gain from Vs to V out when L goes to 0 is always equal to 0 in this particular example with an ideal op-amp. So combining those all together, we have that the closed loop gain is A sub L infinity times L over 1 plus L plus A sub L naught times 1 over 1 plus L. Putting those values in over here, we have minus 1. L was 25, so it's divided by 26. A sub L0 was 0, and that's divided by 1 over 26. So the overall closed loop gain is given by this result here, minus 25 over 26 volts per volt. So let's look at example 2 now. In example 2, it's the exact same circuit, but we're going to change the op-amp. So it's the same as we had in example 1, but our op-amp is now going to be more practical, more realistic. So in this case here, our op-amp model, which is the op-amp symbol shown here, but we'll use a model that looks like this. So it has a differential input impedance of R sub ID. It has a GM times VOI, where VOI is the voltage across that differential input. And it has an output resistance of R naught. That gives us our output V out over here, which corresponds to this one, this node. And we have these values here that R ID is 10 kiloohms, GM is equal to 2 milliamps per volt, and R naught is equal to 20 kiloohms. So the output impedance of this op-amp is 20 kiloohms. You can see that you might get that if you have, if you're looking at the drain connections of a transistor. So you're not going to have a extremely low output impedance. So again, looking as we did before, we want to find Z1. So in this case, Z1 now is going to be the input impedance to that op-amp. So the input impedance that we see looking down through here, and that's just given as RID. So Z1 is equal to 10 kiloohms, which was given here. For Z2, we have the impedance looking back over here. So that's going to be the impedance here, which is R1, in parallel with the impedance looking in this direction, which will be R2, in series with the output impedance looking in this direction, which is R0. So we'll have that Z2 is equal to R1 in parallel with R2 plus R0. R1 is 10 kiloohms, R2 is 10 kiloohms, and R0 was 20 kiloohms. So it's 1 kiloohm in parallel with 30 kiloohms, and that works out to be 7.5 kiloohms. Now we need to find L for this circuit. So we have the op-amp model put in over here. And we've introduced our voltage source, ideal independent voltage source V sub t. It's driving an impedance Z2. And we also have, we're trying to find the gain back to this node over here, V sub R. So the first thing we notice is that the voltage V sub OI, if we look at that, is actually drawn with a negative here and a positive here because it's been, remember there's a, the way we drew it up here for the model is we have the positive and the negative top and bottom. So that would be shown here, positive and negative top and bottom to the V out. But up here we actually have it negative and positive. So there's an inversion here. Otherwise we would have positive feedback rather than negative feedback. So because of this inversion, we actually have that VOI, the voltage here, is negative VT. So the minus of this voltage. We also would like, we're going to need this resistance here. That's just going to be R0 in parallel with R2 in series with R1 in parallel with Z1. So we can write all this out here, and we have that R sub X is what I just mentioned. That works out to be 8.5 kilo ohms in this case. Now the voltage V sub 1 will be this current here, which is GM times VOI, times RX, the impedance we see at that node to ground. So we have that V1 is GM times VOI times RX. That works out to be, remember GM is equal to 2 milliamps per volt. It's multiplied by 8.57 kilo ohms. So it works out to be 17.1 times VOI. And because VOI is negative VT, this is minus 17.1 times VT. Now going from V1 to VR, it's just a resistor divider, where it's R1 in parallel with Z1, divided by R1 in parallel with Z1, plus R2. So we have that VR is just this resistance divider times V1. That turns out to be a gain of 1/3 going from here to here because of the sizes of the resistors. So then we have that VR is equal to 1/3 times V1. We have V1 given by here, which is minus 17.1 times VT. So it's 1/3 of minus 17.1. So it's minus 5.71 times VT. So that's what we really want to find here was VR in terms of VT. And then by definition, L is minus VR over VT, so it's just 5.71. As expected, L is greater than 0, so we have negative feedback. For A sub L infinity, it turns out it's exactly the same arguments as we had before. It made no difference. The fact that we put in a model for an op-amp here, still we'll find all the same arguments hold. And so we'll find that A sub L infinity is still minus R2 over R1. And so therefore it's just exactly minus 1. So in other words, if the loop gain goes to infinity, so if you introduced into this node here into here, we introduce a very, very large gain at this inserted at this point here. Then it acts as an ideal op-amp circuit, and we get a gain of minus R2 over R1, which is minus 1. For the last one, we need A sub L 0, and this now is no longer going to be 0. So we have our voltage source at our input. We've broken the loop right here. So that's now our break, where we have Z2 and Z1. And now we just find the gain from VS to Vout in this circuit. Well, we can start off and we can notice that in this part of the circuit here, there's no signal. So we have basically VOI, but there's nothing that's driving this. So what we have is that VOI will just be 0. So we have that VOI right here is equal to 0. If VOI is 0, then GM times VOI is also 0. So we can ignore this part as well. So we really just have, in this case here, a resistor network. It looks like this. That we need to find the gain from VS to Vout. So to do that, we can find the impedance R sub Y looking into this part of the resistor network. And that's just going to be R sub D in parallel with R2 in series with R0. So it becomes this formula here. Works out to be 7.5 kilo ohms. So that's the impedance, 7.5 kilo ohms is the impedance we see right at RY. We can then find the voltage V1. V1 will be a resistance divider between R sub Y and R1. So we have that Vy is just equal to Ry divided by Ry plus R1 times Vs. So that's equal to 0.429 times Vs. We now know the voltage at V1. To get the voltage here, it's just another resistor divider between R0 and R2. So we have that Vout is equal to R0 over R0 plus R2 times V1. V1 is given by this formula up here. Actually, first off, before we do that, this 2/3 factor is R0 divided by R0 plus R2. And now we can substitute this V1 into here. And we have that Vout is equal to 0.286 times Vs. So we're just multiplying this value by 2/3. So finally then, we have the gain from Vs to Vout when L goes to 0 is given by this value here, or 0.286 volts per volt. We then combine all these known values that we have now, A sub L infinity, L, and A sub L naught, into this equation. We can just write all those values in, and we end up with the gain being negative 0.0858, which is this term here, plus this term, which is 0.043. And that's basically results in negative 0.808, which is almost the same as the one just above. So it turns out this term here, in this particular case, did not really become very important. So that's, in this case, it didn't become too important because our A sub L0 was fairly small relative to 1, particularly when it got divided by the feedback, 1 plus, divided by the gain, divided by the value 1 plus L. So it became a small value, relatively speaking. So in this particular example, A sub L naught did not change the result very much, but that's not always the case. In some cases, it can be very important. So the final example I want to look at in this section is example 3. And we have a transistor circuit here rather than an op-amp now. So in this case, we have an NMOS transistor, M1. Actually, it's just not M1, it's just a transistor. I won't give it a name in this case. It's just a transistor that has a GM value of 1 milliamp per volt and an output impedance of 50 kilo ohms. We want to find the gain from IS to Vout. So we'll have a current input in this case, independent current input coming into this circuit. And once again, we're going to break it at this node right here. So in this case here, we have that the impedance looking into the gate of the transistor is infinity. So Z1 is infinity in this case. So putting it onto the other side makes no difference. And we'll worry about Z2 in a second when we're looking for the next part of it. So Z2 is the impedance looking back here, and we'll need that when we're looking for A sub L0. But for L, we just have the L is the gain from this node to here, and that's going to be the GM of the transistor. Actually, it's negative GM of the transistor, but the minus sign will cancel out. GM of that transistor times the impedance at this node, which will be RD in parallel with R0 in parallel with RF plus RS. And that would also be in parallel with, if we included Z1, then this RS here would become RS in parallel with Z1. But because Z1 goes to infinity, we didn't need to worry about it in this case. So that's the gain from here to here. The gain going now from the V out to this node is just a resistor divider between RS and RF. So we have multiplied by this value here. So right on the circuit, we can actually write down the equation for L. And as I said, the negative sign canceled out because our gain, L is defined as minus VR divided by VT. So if you multiply all these out, you'll end up with L is equal to 7.04 volts per volt. For A sub L infinity, once again, we are putting we're making the gain go to infinity by inserting an amplifier at this node, so an ideal amplifier, effectively, that goes to a gain of infinity. If that's true, then the voltage at this node, the amplifier is over here, will go to 0 volts. So it goes to 0 volts here, which means that there's no current that goes down through RS. So this will go to 0, and all of IS will flow in this direction. This is 0 volts, so the output voltage V out will just be equal to minus RF. So V out, we have that because V out will just equal minus IS times RF, and A sub L infinity is equal to V out over IS as L goes to infinity. So we just divide this, bring this IS over to the left side. So we just bring that over here to the left side. And we have the result is just minus RF. So the gain for this circuit when the loop gain goes to infinity is minus 10K. And that's in units of volts per amp. Now really we have a current as our input and voltage as our output. Now for the final one, we need A sub L0. For A sub L0, we're going to find the voltage, V1, and then we'll find the gain from V1 to V out. So first off, we'll find the gain from IS to V1, to this node here. Well, the impedance that we're going to see here to ground is going to be RS in parallel with RF in series with RD in parallel with R0. So that's the impedance we see at this node, and that gets multiplied by IS to give you V1. So we have that V1 is equal to IS times that impedance, and I said it's RS in parallel with RF, in series with RD, in parallel with R0. Remember, there's a Z1 would be in there as well, but because Z1 went to infinity, we don't have to worry about it. So that works out to be 15.5K times IS, and that's V1. Notice we won't actually need Z2 here. So the impedance looking over here, which was Z2, eventually we'll add that as the resistance over here, but we don't ever need it, so it never gets used in this particular example. So then we need to find, now that we have V1, we need to find the gain from V1 to V out. And as I mentioned, that's just a resistor divider with RD in parallel with R0 divided by RD in parallel with R0 plus RF. So we have that V out is this resistor divider network times V1. We already have V1 from here, so we can make this substitution in to there. So this 0.4545 is this value right here. So making this substitution, this into here, we have that V out is equal to 0.4545 times 15.5K. So A sub L naught, which is the gain from I sub S to V out when L goes to 0, is just multiplying those two together, which gives us 7.05K. And again, that will be volts per amp. So the units of this is volts per amp. So now finally we can write down our overall closed loop gain using these values that we've already found. Put this into that equation above. In this case we'll get minus 8.76K plus 0.877K. So this is about 10%. So this starts to make some difference to it. And so the overall closed loop gain then is given by this value here, which is minus 7.88K volts per amp. And that's the end of the examples for this video. Thanks for watching.